Great, thank you very much. Well, it's such a pleasure to be here celebrating the wonderful discoveries of the Keck telescope in its first 2 decades. I mean, it's just been such a marvelous set of telescopes and associated instruments. And I have the great pleasure of presenting the work that led to the 2011 Nobel Prize in Physics, the discovery of the accelerating expansion of the universe. The prize went to Saul Perlmutter, the leader of the Supernova Cosmology Project, to Brian Schmidt, the leader of the High Redshift Supernova Search Team, and to my postdoctoral scholar, Adam Rees, who was a member of Schmidt's team, who was the first author of the Schmidt team paper. And all 3 gentlemen, by the way, wanted me to express their great appreciation to the very hardworking Keck staff and to all the people who made the Kecks possible and keep them working at such a great level. This is really your Nobel Prize as well. Now, they understood that, of course, without the rest of the team members working in the trenches, they wouldn't have been honored in this way. So they spent part of their prize money flying the rest of us out there to participate in Nobel Week, and that was wonderful. They should have flown everyone associated with the success of the telescopes out there, but there wouldn't have been enough money to do that, and there were limits imposed on the by the Nobel people on how many guests they could have. So, but at least the team members were able to participate in the festivities. I'd like to dedicate this talk actually to my thesis advisor, Wal Sargent, who was one of the great proponents of the Keck telescopes, the 10-meter telescope at the time, and one of the fundraisers for it. And certainly he used the telescopes very effectively and very productively for many years, and he would have loved to be here to celebrate. It was with Wal that I did a study of nearby galaxies with the Palomar-Hale telescope and serendipitously stumbled across a supernova that turned out to be amazingly interesting. It was one of these type 1Bs and 1Cs that Shri briefly mentioned before they were known as such. And this got me very interested in supernovae and eventually landed me in this field of using type 1As as cosmological yardsticks. And it was just an amazing experience, and it all happened with Wal nearly 30 years ago. Well, of course, Vesto Slipher first started systematically measuring the redshifts of galaxies in the teens of the previous century, and he noticed that these lines are redshifted in most cases. Edwin Hubble used Slipher's data as well as distances that he determined through studies of Cepheid variable stars to find that, yeah, most of the galaxies are moving away from ours, and right now, at a given time, the more distant ones are moving faster than the nearby ones. So there's this Hubble law, distance along the ordinate, redshift or recession velocity along the abscissa, and it's a linear sort of relationship. Technically, of course, this is a relationship among clusters of galaxies. Galaxies within a given cluster are not moving away from each other because the clusters are gravitationally bound. We now understand that the redshift is fundamentally a stretching of space itself. It's not that the galaxies are moving through some pre-existing space, but rather that the space itself is expanding. And we are not at the center, at least not in any unique center. No matter which galaxy we happen to be in, we would see all the others moving away from ours, okay? Well, here's a plot of the scale factor of the universe. This can be thought of as the distance between any 2 representative clusters of galaxies, and that distance grows with time due to the expansion. But only in an empty universe would you expect that expansion to be linear, okay, to not change at all with time. But we know that the universe isn't empty. We exist. The Keck telescopes exist. Galaxies exist. So every little volume of matter is pulling on every other volume of matter elsewhere in the universe, and the universe should be slowing down. If the density of the universe is high, then, though it's expanding now, it'll someday stop and reverse its motion. That's plotted in the red line there. So if the average density exceeds some critical density, omega matter is greater than 1, and you get an ultimately imploding universe. If you have a universe that in a sense was thrown at the escape velocity, then the speed approaches 0 as time approaches infinity. This also corresponds through general relativity to a geometrically flat universe. And then there can be the universes that are sort of in between empty and critical. Those are the universes that, in a sense, were thrown at a speed greater than the escape speed. They slow down with time. You can't stop gravity. But the rate of expansion asymptotically approaches some non-zero value. Through studies of galaxies and clusters of galaxies and their motions, the theorists told us that the universe is of intermediate density, omega matter around 0.3. This is what they told us decades ago. But we wanted to see whether this is true by looking at the past history of expansion and seeing whether we could tell which of these paths the universe has actually been following. It's sort of like looking at this apple. If you measure the rate of motion, the speed away from my hand at many different times, you can predict what it will do in the future. Let's look at those graphs early on in time. If we look at time now, that's redshift 0. If we focus our attention at redshift 1, that corresponds to a universe that was basically half its present size. And you can see that depending on what depending on what the universe has been doing, the look-back time, and hence the distance to a given galaxy at redshift 1, depends on the past history of the universe. That distance is smallest in a dense universe, bigger in a less dense universe, bigger still in a less dense universe, and the biggest possible in an empty universe. So this theoretical diagram translates to an observer's view that looks like this. At low redshifts, all the curves come together with the same slope. That's just the Hubble constant, okay? That's the linear Hubble relationship that you see at the lower left there. But at high redshifts, the curves diverge. And so we wanted to measure redshifts and independently distances of galaxies in order to see which of these curves, if any, the universe was following. Well, how do you do this? How do you get the redshifts and distances of galaxies? Redshifts are pretty easy. You can get them from the spectra, all right? Distances are more difficult. You need to find an object in a galaxy of known luminosity. You measure the apparent brightness B, and you use the inverse square law to get what's called the luminosity distance, all right? And this can be hard to do. Oops, didn't mean to quite go that far. You can do it with standard candles, as we call it, Cepheid variables or something like that. But in fact, to get to big enough distances where you see these curves diverge from one another, you need to use something very, very luminous. That would be a type 1a supernova. They can be billions of times the luminosity of our sun, and they're pretty standard because they come from white dwarfs near the maximum limiting mass, the Chandrasekhar limit, which they grow to either through accretion of material from a relatively normal star or perhaps through the merging of two white dwarfs. Now, they're not perfectly standard. They're not all 100-watt light bulbs. There's some dispersion among them. And the work of Mark Phillips and Mario Amui in particular in Chile established that the more luminous ones take longer to rise and fall than the less luminous ones. So if you find a whole bunch of nearby supernovae and calibrate this relationship, then you can apply the relationship to more distant supernovae by measuring their light curves and figuring out, is it a 100-watt light bulb or 120 or 82.5 or what? You can see the great improvement in the scatter that you get by applying this relationship, determined through studies of nearby objects, to an independent sample. Okay? At the top there, you see what you get if you just assume they're all 100-watt light bulbs. At the bottom, you see what you get when you calibrate their luminosities individually. And, by the way, when you take dust and stuff into account. So, the type 1As are really good. All right? The challenge then was to find them in distant galaxies, use their apparent brightnesses to determine the distances of those galaxies, hence the look-back time, compare that with the redshift, and determine the expansion history of the universe. Both teams used telescopes primarily in the southern hemisphere to take wide-angle pictures of the sky and through digital subtraction find the supernova candidates. And here are actual data that went into the papers. The Kecks were of critical importance in getting the spectra. And that was my job actually on both teams. I have the interesting distinction of having been the only person who at one time or another was a member of both teams. In part because I had access to the Kecks. I've been studying supernovae for decades, and at heart, I'm a spectroscopist, so I agree with Shri, spectroscopy. Imaging is cool too, but man, spectroscopy. All right? So LRES, wonderful instrument, fantastic instrument. Hats off to Judy Cohen, Bev Oak, Joe Miller, and others. You can see that in 1 hour, you could get a spectrum of a supernova at redshift roughly 0.5 that's comparable to, in quality to that of a nearby supernova. The Keck spectra were absolutely critical. They showed which of our objects was indeed a type 1a supernova, and the redshifts were used to, and the spectra were used to also measure the redshift. So you had to do this, okay? And in the early days, most of the redshifts came from the Keck telescopes. Here's in October 1996 an IAU circular, and you can see there's a K in that boxed column that corresponds to, actually it's the last column, the K corresponds to Keck. Most of the spectra were from Keck. But we have competition, and in fact at the time, our collaborators in part also had access to the VLT. They got some of the critical spectra as well, especially as time went on and the VLT became better and better. And this is something we need to be aware of. There is competition out there, serious competition. So we've got to keep on investing in Keck, improving the current instruments, making new instruments, keeping us at the cutting edge, because we definitely have wolves and hounds out there biting at our backs, okay? Anyway, here's the punchline. 3 supernovae confirmed spectroscopically, mostly with Keck. Where did they fall on this diagram? Not along any of the curves, but rather a curve that seemed too high. The supernovae were fainter than expected. The implied distances were greater than expected in any self-respecting universe with normal Newtonian or even normal Einsteinian gravity. You can't give a talk about gravity without using the proverbial Newtonian apple, by the way. So here is an excerpt from Adam Rees's notebooks at the time that he was working in Berkeley as a postdoc. He had this boxed thing which said omega matter, negative 0.36. What is this? Are we made out of negative mass material? I don't think so. That's really weird, right? He came to me and he said, Alex, this is what I found. I said, did they teach you at Harvard how to properly measure the brightnesses of objects, how to do photometry? He went back to his office, remeasured the images, got the same result. Brian Schmidt got the same result. Others on our team got the same result. Omega matter doesn't make much sense. But there was a theoretical idea that perhaps did. The cosmological constant, Einstein's supposed biggest blunder, because Einstein believed, as did many at the time, in a static universe. He found that aesthetically appealing. There was no evidence that the sky was falling. Let the universe be static. So he conjured up an effect of unknown origin and no evidence in experimental measurements in the laboratory, okay? And which implied that the density of the vacuum was not only not zero, but of a repulsive nature. Some people found that repugnant. Einstein himself didn't like the idea, and here he is sad that he ever introduced it. Because, of course, Hubble discovered that the universe isn't static after all. Einstein could have been famous had he not introduced this idea. He could have predicted that the universe is in some dynamic state, but instead he insisted on the cosmological constant, despite not liking it mathematically and aesthetically. It was a fudge factor, not a mathematically incorrect one. It was like a constant of integration, but it was of unknown origin, and it had a specific magnitude that seemed very finely tuned. No real reason that it would have been that way. Well, if Einstein were around right now, maybe his reaction would be something like this if he were to see the evidence for the accelerating universe. The evidence was subtle at the time. We had to go out on a limb. It was only a 2.5 sigma event. All right, here are the data, the blue points and the red points from both teams. But we obtained the results independently and essentially simultaneously. And the plot of, in a sense, the density of this dark energy, the cosmological constant along the ordinate, and the density of matter along the abscissa, shows contours that do intersect lambda equals 0 at the bottom left there, but most of the area is above lambda equals 0, and so the teams felt that this was a significant possibility, and they went out on a limb and announced it. And I had the pleasure for the Schmidt team of announcing this in LA in 1998 in February. Okay, so here are the two papers that came from the two teams, Rees et al. And then Perlmutter et al. And this is the work, of course, that was then deemed the top scientific breakthrough of the year by the editors of Science magazine in 1998. With the coming of the microwave background data, Boomerang and others, the area in the lambda matter plane became tighter and tighter, and a lot of people started thinking that, gee whiz, this may well be true. By the mid-2000s, the contours were becoming even smaller, and there were several ways, in fact, to see that there was something weird going on. The microwave background measurements showed the picture of the early universe, the quantum fluctuations that Sandy talked about, and through numerical simulations, you can see the growth of clusters of galaxies and voids. And that growth of large-scale structure also numerically works better if you include repulsive stuff than if you do not. You get simulations that end up looking a lot like the observed structure of the universe. So we're left with this kind of a situation, a universe that is nearly 3/4 dark energy. It may not be the cosmological constant, it might be something else, but it's mysterious. 1/4 dark matter and only 4 or 5% normal matter, of which only a little bit is easily visible normal matter. Now, this is the preferred interpretation. To be fair, I must also say that one other interpretation of the accelerating universe is that GR is incorrect on the largest scales. But that would be tremendously exciting as well. And most of us are not eager to let go of general relativity because of just its beautiful, simple foundations and the degree to which it succeeds with nearby objects like GPS, binary neutron stars, things like that. We also probe the era of deceleration. Here's the plot with dark energy. You had a decelerating universe for a while, and then as the total repulsion started dominating over attraction, you got deceleration roughly 4 or 5 billion years ago. But a probe of that early deceleration was done by Adam Rees and his team. They used the Hubble Space Telescope to find and monitor very, very distant supernovae, and they ended up being brighter than you would expect in a universe that, let's say, was dominated by dust or by evolution of the white dwarfs, masquerading as acceleration. The spectra for those objects came largely from Keck as well. Here's from a paper by Allison Coyle and others, supernova 1999 FV at redshift 1.21. So here's the paper in 2004 showing the Hubble diagram out to redshifts of 1.5, 1.7. Then by 2007 we had a bunch of these things, and here you can see the era of acceleration out to redshift 0.5 or so, 0.6, and then the era of deceleration. And evolution of the supernovae or high redshift gray dust would have given a different set of points. And so this was very, very important in confirming that we had really found an acceleration. Interestingly, a universe going from deceleration to acceleration is known mathematically as a jerk. Any change in acceleration is a jerk. So the New York Times headlines that came out were a cosmic jerk that reversed the universe. And here's my former postdoc, Adam Rees. So I started getting these phone calls. Hey, who's this jerk you work with who reversed the expansion of the universe? And his mother didn't really like that very much. Anyway, so we're left with this weird universe. And the darker energy is important because, it's 73% of the contents of the universe. We had better understand it. And it perhaps provides clues to the unification of quantum physics and gravity, because it's widely thought that the dark energy is a quantum effect that manifests itself everywhere in the universe and thus dictates the dynamics of the universe. And the origin and nature of the dark energy is perhaps the single most important observationally motivated problem in physics today. And the supernovae were the ones that led to this discovery. How will the universe end? Well, that I can't quite tell you. If the dark energy remains repulsive with time, then the universe will expand faster and faster and faster with time. And so if you want to see galaxies like this with your very own eyes through a telescope, you'd better do it soon, within the next few tens of billions of years, because beyond that time, those galaxies will have been whisked away to such great distances that you won't see them, even with the Kecks, even with the 30-meter telescope. On the other hand, we don't know for sure that this is how the universe will end, despite the fact that there's no question mark at the end of that statement, because it's possible that the dark energy will someday reverse in sign and become gravitationally attractive, as did the inflaton of the early universe, which later became us. You, and you, all of you helped inflate the universe to its present gargantuan size. But that inflaton did not remain repulsive forever. So it's conceivable that today's dark energy will someday turn around as well. And if there's enough of it, if omega total is a little bit bigger than 1, then ultimately we might recollapse. But the betting, I like the cosmological constant because I like the multiverse. I think the vacuum energy is just one of these things. That's what it is. And if we lived in a universe with a big vacuum energy, then we wouldn't be around talking about it. So it's one of the many things that had to be just right. So whatever. Well, in the last few minutes, I just want to give you a glimpse of Nobel Week so you can see kind of what this whole thing is. We arrived on December 6th at this wonderful hotel. The laureates get these beautiful limos with a driver. I could just sort of pretend, okay, but anyway, you know. Nobel press conference where Saul, Adam, and Brian discussed the work along with the economists and the chemist. It was really fun to be there just to celebrate. The next day, the Nobel lectures where all 3 of these gentlemen discussed their work. Wonderful to see. Then that afternoon, the Heisey team held a celebratory lunch where we all kind of got together again. It was a marvelous reunion. One of our team members, unfortunately, had passed away some years ago, but otherwise, all the rest of us were there with our spouses. My wife, Noelle, came up with an interesting T-shirt, Dark Energy is the New Black, which she gave to the participants. And at the same time, Saul's group was having a celebratory lunch as well, and I couldn't clone myself and become a quantum entangled particle at both places. So I went with Schmidt's group, which I consider to be my primary association, even though I collected lots and lots of redshifts and supernova spectral types for Saul's group as well. December 8th, that night, Nobel Prize concert in this amazing concert hall where the ceremony itself was held a couple of days later. Then the next day, I believe it was, lunch at various embassies. We went to the Australian embassy because Brian now lives in Australia. That evening, Nobel Foundation reception at the Nordic Museum. I mean, there was just so much pomp and circumstance on this whole thing. That was just so much fun. And Richard Ellis was there. He can tell you about it as well. Nobel ceremony, December 10th. By the way, you had to have a special bar-coded ticket. Otherwise, you couldn't get in. Also, if you did not have white tie tuxedo, you couldn't get in. So if you had just a regular American tuxedo, you know, you'd be kicked out. So everyone had to be there properly dressed. It was a lot of fun. I've shown you this photograph right after the awarding of the Nobel Prize. Then the banquet, oh my goodness, you know, in between the different servings, dancers and, you know, jugglers and all kinds of stuff. And the Swedish people are looking at this whole thing on their TVs, kind of like we watch the Super Bowl. And I heard making fun of the etiquette of the Americans primarily. But anyway, we got these little gold coins that look like the Nobel medal. Anyway, it was just a lot of fun. There's Richard and I after the banquet, and then Noelle snuck in afterwards because even though there were 1,400 people there, not everyone could get in. Then a big ball that evening in the Nobel in the banquet hall right above it, and then a party put on by the students that lasted all night in this, you know, haze-filled room. It was really a lot of fun. And there, the supernova cosmology project team met as well once again. So then December 12th, we kind of had a symposium. Both teams got together and everyone got to speak, giving their inside views of what happened. and we all got together for a final team photo. Some people had left by this time, whatever. A celebratory dinner that night, both teams, spouses, friends. Mount Mountain from the Space Telescope Science Institute was there. Just a wonderful, wonderful evening where a bunch of us gave toasts and little miniature speeches and things, and we got together for a final photograph. Anyway, it couldn't have been done without the Kecks. It really couldn't have been done without the Kecks. And we will continue to use the Kecks to pursue this field by measuring more accurately the expansion history of the universe, by understanding in more details the Type 1a supernovae in order to better improve their utility as cosmological yardsticks. So I'm very excited about the future of Keck and using Keck to continue this work. Again, a huge thank you to the W.M. Keck Foundation, to all the donors who made the instruments and the operations possible. For example, the University of California pays a lot of the operating funds. To Kara, to Jerry Nelson and the entire project team. To, of course, Hawaii, NASA, NSF, and to the very, very hard-working staffs of the Keck Observatory, the Caltech Optical Observatories, and the UC Observatories. Thank you very much. Congratulations to all those people there. It was really your Nobel Prize as well. Thank you.